the new topic. This is from the last week's slide, right? So now what we are considering is, again, external magnetic field pointing up B0. But now I have a rotating magnetic field. This is horizontal on the XY plane, but it is rotating about the origin on the XY plane. Is that okay? So the magnitude is constant. Total magnitude is constant, except that the angle is changing. And how do we model this? So I think I should have given you this as the first line. Basically, this is the horizontal component. I call it B perpendicular. It equal to a constant number, B perpendicular, times cosine omega 1t plus phi x hat plus sine omega 1t plus phi y hat. What is the magnitude of this vector? Perpendicular, just be perpendicular, right? Because the x component square plus the y component square, these two equal to 1, right? Sine square plus cosine square. So this is b perpendicular square, right? So take square root, so that is the magnitude. So now you trust that this one is a vector rotating on the xy plane, right? Because it's a function of time. Omega keep changing, right? So what should be the Hamiltonian of this? Again, the Hamiltonian should be the addition of the vertical component and the horizontal component. I feel that I might jump a little bit, right? So let me just remind you what's going on. Basically, the total Hamiltonian is negative mu dot B, right? And what is mu? Mu again is just the gamma times h bar divided by 2 times the s, right? The spin. And what is B? B again, B is what? I can call it B perpendicular plus B0 z hat. Is this okay? Right? Just these two, I just add these two together, right? Sorry, this is no, I should not divide. This should just directly the Pauli matrix actually, right? Not the spin. Where h bar divided by 2 times the Pauli vector is the spin vector. So this one, what do I have, right? If I look into this, of course, I have sigma x, sigma y, sigma z, right? 3 component, x hat, y hat, z hat. And this one, of course, I also have x, y, x hat, and y hat, right? Correct? Yeah. So when you do the dot product, of course, then I will get the h bar omega L divided by 2. This is because of the dot product of the z component. You just take it for granted because you need to go through a few steps substituting all these parameters. But eventually it's h bar omega L divided by 2, which we derive in the Larmor precession already, which we studied earlier, h bar omega divided by 2. This is the Hamiltonian. Let me see if we have this here, which is this one. EMB0 is omega L, right? So h bar omega L divided by 2, right? So that is just what we are using earlier, okay? Now then, this one, we just do the dot products. Then, of course, again, we just bx, the x component, times the b sigma x, and then y component times sigma y. And bx component is what? Cosine omega 1t plus phi, right? And that's times b perpendicular. And then the by component is sine omega t plus phi times the b perpendicular, right? And this is h bar divided by 2 omega is because of this term, right? Okay, so we come up with this. Is that okay so far? It's all math, a little bit messy, but just have a good tracking. That will be okay, right? Then we define two parameter, two quantity. One is called the Pauli racing ladder, okay? Is sigma x plus I sigma y, okay? Just a definition. right? For example, you see this one, sigma x plus I sigma y give you 0, 2, 0, 0. You see that if I apply this to a lower stage, 1, 0, it will give me the 0, 1, it will give me 1, 0. It raised the states, raised the level. And similarly, this one is going to lower one level if you apply to a state. Of course, it has a 2 in front, not exactly, but this is what they call the raising operator and the lowering operator. You will see this a lot. Later when we talk about simple harmonic oscillator, again, you will see the raising and lowering operator. Okay, just a definition. And because of this, then what is sigma x? Right, you just add sigma plus sigma y, then I get rid of I sigma y, right, and divided by 2, right? This one plus this one divided by 2 will give me sigma x. And then this one minus this one divided by 2, I will get sigma y. Is this clear? Okay. Okay, and I also define another quantity. This is also the rapid oscillation frequency. But now I use capital omega R. That is because now the electric field, this field is not the same as the field before. This time, I have this B perpendicular times gamma, that will be the omega R. Before, it is actually the omega R, I did not write here, is, if you remember, this omega R is equal to E divided by M, B1 divided by 2. It has a 2. We divide it by 2, right? And of course, this is actually the gamma times B1 divided by 2. This is gamma. Of course, I need to put an absolute value because gamma is negative. Right? Whenever you see E divided by M, it actually is gamma because gamma equal to E divided by M times G divided by 2. For electron, it's negative E divided, negative 1. Okay? Yeah. But anyway, the point is that let me show you again. This is gamma times B1 divided by 2, maximum magnitude. But this is just gamma times B perpendicular, not divided by 2. Right? Because now we have a different pattern of field. It turned out this is the rapid oscillation frequency in this case. Okay, so I define this quantity, then I plug in, right? So this is gamma B perpendicular because it's negative, gamma is negative, so this is just omega R. I keep H bar, then I have 2. I am going to take the 2 from what I'm going to substitute because I'm going to substitute this one by this guy, right? So let me start the math again. So from here, what I got is, what is sigma x? Quite a lot of word. This is cosine omega 1t plus phi. This is what I'm doing. I'm continue to substitute this one. Cosine omega 1t plus phi. Is okay? And then times what? Sigma x, right? But sigma x, I'm going to substitute with sigma plus sigma minus. Okay? Because sigma x is sigma plus sigma minus divided by 2. I take this 2 out. Okay? And then I continue to do the rest. I have sine omega 1t plus phi, and this time is sigma plus minus sigma minus. However, I need to divide it by 2i. By I, right? By 2i, but I take the I out, right? So this whole thing is divided by I. So I just look here, right? This one is divided by I. So this is pretty messy. And I jump in my notes. So then what is this? Now, cosine omega it right? Yeah, my cheat sheet is completely messed up. So now I'm going to convert this to exponential. Should I spend the time to do this? Let me just convert this to exponential, right? So this is the h bar omega r divided by 4. And what is cosine? Cosine is e to the power omega 1t plus 5 plus exponential negative omega 1t minus 5, right? I is only for the sine term. You mean this one, right?
No, I mean.
Oh, yeah, sorry. With the I in front. With I. You see what he mean, right? Because I omega. Okay. And let me put the I at the bottom, right? At the end, right? And then this whole thing is going to multiply by sigma plus plus sigma minus. Okay. And then I do the same thing for the, now I've divided by I, I'm going to only do negative I because 1 divided by I is negative I here, divided by I, negative I. So what do I get here? I get exponential I omega 1 t plus 5 minus exponential I will just call this negative I exponential, the whole thing. I just do a bracket to save time, right? And here, actually, I forgot that I need to divide by 2. The whole thing need to divide it by 2, so I just multiply this by 2 here. And then the whole thing times omega plus plus omega minus. Very confusing. I'm sorry for that. Is this okay, what I'm doing? Yeah.
Can you repeat the green line?
The green line, right? So you have cosine omega, the whole bracket, right? Cosine equal to exponential I something plus exponential negative I. That is what I have here. And then this times sigma plus plus sigma minus. And then I have the sine, but this whole thing divided by I. So I put negative I first in front because this is 1 over I. And then again, sine is exponential this thing minus exponential negative I this thing. And then the whole thing times sigma plus sigma minus.
Then also the I from the sine.
Yeah, I keep missing it. Yeah, thank you. You also need to divide this by, just divide the whole thing by another I, right? Because it is exponential minus exponential divided by 2I for sine. I gave you a lot of trouble. So sine theta equals to exponential I theta minus exponential negative I theta divided by 2I. Yeah. You mean this one? Yeah, only the sine part, only this last term divided by I. Because of this. Okay, now let's just collect the term. My goal is to have a plus and minus. You look at this plus, right? So this plus term is going to have this one and this one. But then here I have a minus, right? So this plus also have this one and this one. So this 2 is going to get cancelled because this is minus 1. And then I have 2 of this minus term, right? So basically what I'm saying is now I have Is this psi? No, this is Hamiltonian. Now I have hi equals to h bar omega perpendicular divided by 8. Right, I have this one. And then now I have two terms, right? This two term has sigma plus times this negative term. So I have sigma plus times 2 exponential negative I omega 1t plus phi. Is this okay? Yeah? Let me say again what's going on. I have a plus term, exponential. I have minus term, right? I have a plus, right? And then minus e to the power plus e to the power minus, right? And then for this plus, sigma plus, I'm going to distribute to this 2. This sigma plus distribute to this 2. But this is negative. Negative I divided by I is negative. So this term will get cancelled. The plus 1, right? And then the negative will stay over because negative times negative equal to 1. Right? You just try to do it. Then you will get this equal to sigma plus times 2 exponential negative term. Is that okay? Then similarly for the negative one, right? Sigma minus, you will get something similar, right? So now, I also have a typo here, I'm sorry. This one is not plus, right? This is minus because this part is the sigma y. Sigma y is sigma plus minus sigma minus, okay? So it will have the opposite effect because this is plus, this is minus. So this term will be gone, the negative part will go. This one will be kept, right? Because this is minus, so I have plus here. This has a minus here, epsilon minus, but then this is, so minus, and then this is also minus, so I become plus, negative times negative, right? Because this is negative, so when they multiply, you become plus, right? So you will keep this term, okay? So this one is going to be plus sigma minus 2 exponential, and then the plus I term, right? I try to keep it. Yeah. Yeah. We try to multiply it out, and then we cancel those terms. Simplify it, right? So, and then the 2 is going to cancel with 8 again. So let me write this again. This is h bar, omega perpendicular divided by 4. And then you have this term, exponential negative I omega 1t plus phi sigma plus exponential I omega 1t plus phi sigma minus. Is this okay? Yeah.
Is that term at the bottom, is that part of the same line?
Part of the same line. Yes.
Okay.
I'm so bad here. The same line. And then the whole thing multiplied by this one. Okay? So eventually you get this one. Okay? Now, then our idea is this. This is complicated. Hi is time dependent. It depends on t, right? And this is expected, of course, because our magnetic field is time dependent. But then we will ask one thing. Although it's time dependent, but it depends on the time in a coherent way. What if we use the rotating frame? You see that something is oscillating around about the origin on the xy plane. If I follow that vector, then it won't be time dependence for me, right? This is just the idea. It's just that you stand on the merry-go-round. If you stand outside, you see, wow, the merry-go-round is rotating. You jump on the horse, then you don't see it's rotating, actually, if you cannot see the outside world, right? Of course, you feel centrifugal force, all these things, but you don't see it's rotating, right? So we want to go to the rotating frame, because once if that is the case, then we can integrate easily, integrate the Schrodinger equation easily. So that is the idea of using the so-called rotating frame. Okay, so you hear a lot about the rotating frame. But now the problem is we need to go through some nasty math again to get what is the expression of the Schrodinger equation in the rotating frame. Once we get it, then we get some very nice solution. Okay, so let's start with that. But before that, let's think about rotation, right? Rotation is what? We already discussed earlier. Rotation is just like rotating in the hyperspace or whatever. It's a unitary transformation, right? So when you do a rotation, what does it mean? In this frame, in this particular rotating frame, rotation, it just means that if I have the alpha in my vector, right? Alpha of my vector. I'm talking about my general vector. Psi equal to alpha 0 plus beta 1, right? In the rotation, we know that alpha become alpha times e to the power I, negative I, omega 1 divided by 2t. That is how you do the rotation on the Bloch sphere. Okay? And beta becomes beta e to the power negative I, omega 1, plus, right? Beta should be plus, right? Do you see this? Because what is omega 1t? Omega 1t is just the angle you have rotated, right? So this part is just the delta theta. Right? For a state. Let me quickly, before you ask. This is the state phi, right? When I rotate it by a certain angle, it's just phi plus a delta phi, right? I should not call it theta, delta phi, right? So let me be more specific. Should not be theta, should be phi, delta phi. For a rotation, right? Do you agree? And so, of course, the coefficient will go with negative I delta phi divided by 2. And delta phi, of course, omega 1t, because omega 1t is the rotating frame. Right? You have a question?
This is more like a perturbation.
Is more like what?
Like, give some equation before, like the perturbation, like when psi is t, it deviates and there's some exponential like this one.
No, this is not this one. I think you are asking, is this equal to this one, right?
Yeah.
They have the similar origin, but we are not talking about try to represent as the basis. Here I'm only purely talking about what happened if you follow the rotating frame. Okay, so now I have not done about the rotating frame there. I should be specific. This is rotation of state. If you rotate a state following this rotating frame, isn't that you will rotate by omega 1t after time t, right? So that's what I'm trying to say. But they are similar. They have similar origin because they both due to rotation. But their eigenstates is because of the magnetic field pointing up and your precessing, which is rotation. That's why you get omega L, right? But here is just purely rotation. Even you don't have the B0 pointing up, I still can do a rotation, right? No, I just rotate transformation. I'm not really saying that it's physically rotating. I'm just saying that, okay, what if I do something to let it rotate? How will you represent the state? That is what I'm talking about here. So, because of this, what is the U? Right? Naturally, you will see that, okay, then the rotating matrix, the unitary matrix, then it can be written as e to the power negative I omega 1t divided by 2 sigma z hat. This is U.
So now we're going to do transformation.
Yes. I try to first tell you how it looks like after rotation. And then I say that is the same as applying this transformation matrix. Let's do a quick check if I'm correct, right? For example, this is e to the power r negative I omega 1t divided by 2. And what is sigma c? 1, 0, 0, negative 1, right? And this is diagonal. I can just exponentiate it directly. Then I get e to the power negative I omega 1t divided by 2. And this is e to the power positive I omega 1t divided by 2, 0, 0. Correct? Now, isn't that, if you apply to the 0 state, it will get negative I omega t divided by 2. Apply to the 1 state, the matrix, it will get plus I omega 1 divided by 2, right? So this is the correct transform matrix to get this rotation. But I'm rotating the vector. But now what I care is what? Rotating the frame. So what is the difference between rotating the vector and rotating the frame?
Not a complete rotation.
No, I mean, it's just like, what's the difference of you move the 4 backward? I mean, I'm on the merry-go-round. What's the difference? You rotate the merry-go-round backward compared to I walk backward. They are inverse of each other, right? So I go forward by 15 degrees is the same as the coordinates go backward by 15 degrees. Yeah? So based on this, then I claim that the rotation of the frame must be U dagger. Okay? Because U dagger times U equal to 1. Because it's unitary. Okay? So U dagger equals to what? E to the power I omega 1t divided by 2 sigma z. Okay? Because it's U dagger, right? You take the transpose and the compressed conjugate. So here, basically, that is what we say, right? If we go to the rotating frame, right, there's a 1, 2, 3, right? We find all the matrix at the rotating frame. Right? So now I change the frame. Instead of the LED frame, what they call LED frame, I'm trying to describe all the physics by following this rotation. Right? So in that case, I'm not advancing the qubit. The qubit is actually going backward because now it is moving forward, right? The frame. So instead of this qubit going, for example, anti-clockwise, now I'm seeing that the coordinates is going anti-clockwise. Isn't that is equivalent to the qubit going backward? Correct? Yeah. So because of this, right? This is the rotating frame. So we are going to call this URF. Okay. So the URF is the dagger of U. Okay? So at the rotating frame, how do we get the new states then? We have the new state is equal to the URF times your original state. Okay, so now you describe the state in the left frame. For example, you say this state is at this position. Then what is the coordinates of this in the rotating frame? You actually should see this keep going in the opposite direction. And this is this equation, right? And how about the operator? If you remember the operator, any operator, it will become the U, R, F times the original operator times the dagger. I think we mentioned this before. If not, you take it for granted. We mentioned this before. I mean, if you forget, you take it for granted, right? So now I go into a new frame instead of the old left frame, right? It's easy to understand for the states. Again, for example, I'm walking forward. Now you want to use my frame to describe me, right? Then you probably say that I'm not moving. Because the frame is, the coordinates is processing at the same speed as me. Then it's not moving. If I actually did not move, it's still progressing at the same speed, you will say that I'm going backward, right? So this is basically what it is. I'm walking forward, then in this rotating frame, you say that I'm not moving. Okay? But how about the force on me? Right? Then the force will be different. In order to describe this, of course, this is not the force, but just want to, as an example, right? You won't say that I don't, because if you are accelerating, for example, I was accelerating. No, I'm not accelerating, but you have a frame which is accelerating. Then you will say that I am accelerating, right, in that frame. Then, but no force is acting on me. You need to come up with a fictitious force saying that, oh, actually, I have a force which is pushing me. This is similar to the relativity, right? The gravity is equivalent to acceleration, right? So, then I try to say this, but after all, this is just a simple linear algebra, right? So you rotate this one, and then all your operator need to have this so-called similarity transformation. Okay, you need to transform them accordingly. Okay, and this is the equation, right? Now with this, then we can start talk about the Schrodinger equation. So in the rotating frame, right? First of all, the original equation is this. It is I h bar partial psi partial t equal to h psi. Okay, this is the total Hamiltonian, which is this one. Now in the left frame, you say, okay, the state should evolve as h times the state with this equation, right? But I don't want to describe here because this is complicated. You look at this h, it's time dependent. I don't want this, right? So what should we do? We now will go to the rotating frame, but we need to be very careful to transform it, okay? So first of all, then I will say, what is the, consider I h bar partial the rotating frame state. Okay, now describe the state in the rotating frame. Okay, so what is that? Now, based on this, you need to plug in what we just said. What is psi RF? It's U RF times psi. Do you see that? Because original is U RF times psi equal to psi RF, right? Or just plug in the math, okay? But both of them are time dependent because the rotation, the unitary matrix depends on time, right? It has e to the power negative I omega L divided by 2t, right? So you just use the differentiation law, I h bar partial U R F partial t, and then the whole thing applied to psi plus I h bar U R F partial psi partial t. Okay? So what is this? Now the first one, we keep it, is I h bar partial u r f partial t psi. But how about the second one? The second one, we know that I h bar partial psi partial t equal to h psi. So I'm just to plug in. This is going to be equal to u r f times h psi. Right? Of course, you know that this is a matrix, right? H and u r f, this is a matrix, right? And this is vector. And this is matrix. It's just time varying matrix. Okay? And then let's continue. Right? I need to keep looking at my cheat sheet. Then continue. I'm going to plug in this psi, right? So it's a little bit funny. I keep changing because the goal eventually is a high side. I know that what it will be. So what is this psi? Again, I want to go back from the left frame to the rotating frame, right? So let's remind ourselves. Psi RF equals to U RF times psi, correct? Then psi equal to U RF dagger RF, right? Just go back, right? Because they're inverse of each other. So because of this, then I have I h bar partial U RF. I don't have enough space. Let me write it again. Equals to I h bar partial U R F partial T, but I will put U R F dagger psi RF. Okay, and then plus U R F H. I want to go back to the rotating frame again, so I again put this one. Do you see this? Let me just circle that. This one come from this, right? This one come from this. Is that okay? All I did just plug in what is psi. Psi equal URF dagger psi RF. Okay? And I'm going to group them. Then I say, let me use another color. This is I h bar partial URF partial T. And I keep did I do wrong? Okay, I swapped them. Yeah, that's okay. I keep the U R F inside, right? And then plus U R F H U R F dagger, and then the whole thing about apply to psi. So I have a mistake you did not tell me. Do you see a mistake I made just now? In the red line before this one. What mistake did I make?
Did you swap psi RF and psi?
I forgot to put RF here. Yeah, right? This one should be RF because its psi becomes this, right? So I take out this RF. Then I have this part, right? I'm going to call this whole thing as HRF. Now, a lot of math, but yeah, if I give you in the exam, you won't be able to do it. I won't be able to do it because you need a lot of practice, and maybe these are not the best way. But here, just to show you that how you do it, right? So I start with IH bar, and then I look at the state in RF, and then I just go through all this substitution. Eventually, I have something times psi RF. The original coordinate is the rate of change of psi equal to h times psi. Now I have an equation tell me the rate of change of psi in RF in the rotation frame equal to something times the state. So this is not a new Schrodinger equation, right? Except that now I express is Hamiltonian as a combination of what I know, including H, including the transformation.
So that Hamiltonian is in the rotating frame.
The whole thing is in the, you cannot say in the, how do I say? It's just a matrix. Do not say that it's in the rotating. Yeah, you can say that is the effective Hamiltonian in the rotating frame. Yeah, then it becomes a new Schrodinger equation. Okay? Now, so now my goal is to solve this equation, right? So how do I solve it? Solve I h bar partial psi RF divided by partial t equals to HRF psi RF, right? And this is what we have done so far. We come up with this, right? It's just that this is very complicated. But we will show that this is not really complicated. So let me label it. This is 1, this is 2, right? Let's say this is 3, this becomes 4, right? And this becomes 5, right? All this step. So let's look at it one by one. First, what is partial URF partial T, right? So we want to look at this one. Partial URF partial T. What is URF? This one is URF, right? So what is this one partial T? Maybe I just spell it out, it will be easier. It means partial T exponential I omega 1 divided by 2 sigma C. And sorry, there's no C here. I don't know why I put C here in my note. This is just a matrix, just sigma C, right? Sigma C. Is that okay here? Are you okay with how I substitute here? Because this is URF. Right? This is URF. We found before. URF equal e to the power I omega 1t divided by 2 sigma c. So when you do a differentiation, what you get? Just a regular, because it's diagonal, very easy, right? It's just equals to I omega 1 divided by 2 sigma z, right? And then URF. Should there be negative here? Very good. Do we have negative here? Because URF is the dagger of U, right? U has negative, so now it doesn't have negative. Yeah. Okay, so this is this, right? So with this, then what is the first term? I h bar partial URF partial T times URF dagger equals to, it means that I need to apply I h bar to this guy and also apply URF dagger to it, right? What is URF times URF dagger? 1 identity, right? But it's unitary. Or what is rotating forward by theta and then rotate backward by negative by theta, right? So, and then that gives me negative for 2i. So this is negative omega 1 h bar divided by 2 sigma c. This term is very familiar to us. Omega 1 h bar divided by 2 sigma c. It's just equivalent to an effective Hamiltonian in the z direction, magnetic field in the z dimension, doing the precession. But doesn't matter. The main point is this is not temperature, not time dependent, right? So that is the first term, right? So how about the second term? Second term is a little bit complicated. What is H?
Wait, did a minus get added? No, that's just like.
It's minus because I times I. Because I'm trying to look at this term. Yeah, yeah. Okay. Okay, so actually now let's look at the total Hamiltonian. So what is H? Let's look back, right? Just recall, actually, my notes is really. Just recall, what is the total Hamiltonian again? Not in the rotating frame. Is H equal to H bar omega L divided by 2 sigma C that we proved earlier, H bar omega R divided by 4 e to the power negative I omega t plus phi, and I should have a 1, right? Sigma plus, and then plus e to the power I omega 1t plus phi, sigma minus. I just try to recall what we did. Is this okay? This is the total Hamiltonian we prove here, because HI is this term, right? Sigma plus, sigma minus, right? And then, of course, I need to add back the H0, right? Which is H omega L divided by 2 sigma, right? This is the original Hamiltonian, okay? Then what is HRF? You see that HRF is just this term, extra term, plus the transformation of this term. Do you see that? Yeah? So this is just equal to what? How do I do that? Let me just write it out. Negative omega 1 H bar divided by 2 sigma C, which is this term, right? Plus the transformation URF H URF dagger. Okay? HRF is just this term, right? Plus URF H URF dagger. Make sense? But how about this one? When you apply URF and URF H dagger to this whole thing, what do you get when you apply to this term? Because sigma C is diagonal, so when you have a not diagonal, not just because it's diagonal, because URF has sigma C. Look at this, exponential sigma C. So it commutes with this part. So I can just swap them. What I'm trying to say, maybe I need to get more space, right? So let's do step by step. I did not consider this in my cheat sheet. So consider, let's do this one by one, right? URF times sigma C times URF dagger equals to URF dagger times sigma C equals to sigma C. Are you okay with this? Why I can swap them? They are matrix. Why I can swap them? Because URF only has sigma C. So sigma C commute with sigma C, right? It's exponential sigma C, but you do Taylor expansion, it's just all sigma C squared, right? So sigma C times sigma C is equal to sigma C times sigma C. So I can swap these two matrix, and then this 1 times 1 equal to 1. You cannot swap the matrix without any reason. This is the reason why you can swap them, okay? So this one becomes sigma C, right? So basically, what are we doing? Basically, then we say that this term, I can just keep it. This term, I can just keep it, right? So So then I have HRF equals to negative H bar omega 1 minus omega L divided by 2 sigma C. Why? Because first I have the original Hamiltonian omega L divided by 2 sigma C. This is due to B0. And then this term gives me omega 1 H. This is sigma L. This is not sigma C. Oh, no, this is sigma 1. I'm sorry. I'm sorry. Actually, I don't need to do this transformation. I completely screw up. Sorry. What is HRF? Let's look at this. What's HRF? HRF equal to this term times this term, right? Is that okay? And what is this term? We prove that it is negative omega H bar divided by 2 sigma Z, right? So this is here already. Only this H part we need to transform, right? But what I'm transforming should be omega L, not, so that's why I said should be omega L, not omega 1, right? Because I apply this to H. So as a result, I have negative omega 1, so I have negative omega 1, and then this is plus, right? So it becomes negative omega L. Yeah? And then for the whole thing, it becomes this. H bar omega L divided by 2, right? I'm just copying this term, but then I apply the transformation to it. E to the power negative I omega 1t plus phi URF sigma plus URF dagger plus e to the power I omega 1t plus phi URF sigma minus times URF dagger. Let's look at this one more. I know I am confusing you guys. HRF is what we want. And HRF, we already proved that it has two terms. One is this term, which does not exist. We don't have the magnetic field here. This is very useful. That's what they call virtual Z gate. That even you don't have vertical magnetic field, you see that effectively it is going to precess when you are in the rotating frame, right? And plus this term, which is just the transformation of H, right? Here I try to show you the H has these two parts, so transformation of this part is easy because they commute, so I just take this out. As a result, I get this term. But then the transformation for the rest is not that straightforward. I just apply the H to here, to the sigma plus and sigma minus. Okay? Any questions? I know this is ugly, and because of time, then I decided to skip the detailed math, but you can prove that, right? Prove yourself. It's not easy, not difficult. That URF sigma minus URF plus equal to e to the power negative I omega I omega 1t sigma minus. Okay? And similarly, URF sigma plus URF dagger equals to e to the power I omega 1 t sigma dagger. Okay, so you can prove this. Maybe let me quickly prove it. For example, okay, let me see. We already know what is sigma plus, right? For example, sigma plus is what? 0, 2, 0, 0, right? At the beginning, we'll talk about that. And what is URL? We also proved that is e to the power, which one? URF is plus. So URF is plus, then this is negative, this is I omega 1 divided by 2t, e to the power negative I omega 1 divided by 2t. This is URF, and this is e to the power negative I omega 1 divided by 2t. This is 0, e to the power I omega 1 divided by 2t, right? URF is what? URF is positive, right? So because of this, the z is 1 and negative 1, right? So I get positive and negative. And then the dagger is negative and positive, right? So this is what we have here. We are requesting for this, right? URF sigma dagger, sigma plus times URF plus, right? So this is what I have. If you go through the math, this times this, you only get one term, which is 2ei omega 1 divided by 2. Okay? And then multiply this one, right? And then you do one more multiplication, what do you get? You only get the last 0, 0, 0, 2, e to the power I omega 1 over 2t, right? There, I did something wrong. Should it be plus or minus? Let me check again. This is 0, and I get this 0. 0. No, this is wrong, right? It should be at the top, correct? When I do the matrix multiplication. Because this row times this row give me 0. And then this row times this column give me 2 e to the power omega 1t, right? Because they are half, then I multiply them together. I omega 1t instead of divided by 2, right? This row is 0, so of course the rest will be 0, right? And what is this? Yeah, exactly. Just e to the power I omega 1t times sigma plus, correct? Yeah, so here I prove what I said here. Yeah, this is what I said here, right? So you can try this one, right? I'm able to do this. Now, then what is the total Hamiltonian now? HRF, the first term is negative h bar delta divided by 2 sigma z, where delta equals to omega 1 minus omega L. Do you see this? Omega 1 minus omega L, delta, right? Something called detuning. And then plus h bar omega L divided by 4. Now, look at this. If we say this one transformation sigma plus becomes e to the power I omega 1t, then you multiply to this one. Isn't that you cancel this one? Because this is negative I omega t. Same for this one. You multiply this one, you cancel this one. Because this is negative I omega t, this is plus, right? So what you get is this. What you get is e to the power negative I phi sigma plus e to the power I phi sigma minus. It makes sense? Is there any time dependence from this perspective? No, right? So very good. But we still have sigma plus and sigma minus that we don't like. So what we can do is go through some more math. And of course, a little tedious. This one is what? What is cosine? What is e to the power? This is cosine phi minus I sine phi, right? And what is sigma plus? It is sigma x plus I sigma y, correct? And then how about this term? Cosine phi plus I sine phi. And then sigma minus is sigma x minus I sigma y. Okay? I'm only talking about this part. Okay? And what do we get? You just go through the terms. Cosine phi times sigma. And this is cosine phi times sigma. So I have two of them. I do have 2 cosine phi times sigma x. But sigma x times negative I sine phi, sigma x times plus I sine phi, they got cancelled. I sigma y times cosine phi, negative I sigma y times cosine phi, cancel. But then this one, I times I is negative 1. So this term gives me sine phi sigma y, right? These two terms. How about these two terms? I times negative I also plus, so I get another 2 sine phi sigma y. Okay? It's just a matching, right? So eventually, you get the Hamiltonian to be negative h bar delta divided by 2 sigma z plus h bar omega r. But I have 2, right? So this is divided by 4 because I have 2 here, right? Times cosine phi sigma x plus sine phi sigma y. A very neat equation, not time dependence, nothing to do with omega 1. It depends on the detuning. How is your Larmor frequency different from your rotating frequency? And also, what is the initial phase of your magnet, of the horizontal magnet, right? This one can be written as what? H bar omega a vector divided by 2 dot sigma. Is this something similar? Isn't that this is just like the Larmor precession? H bar, regular, right? You just have a omega, a vector, which is the angular frequency, omega L, right? Times the, what do you call the Pauli vector, right? Where omega equals to cosine phi omega r sine phi omega r negative delta, right? Because x is cosine phi omega r, y is sine phi omega r. And then you have negative delta. You just plug in. You will see that now the Hamiltonian is the same, very similar. Remember what is the Hamiltonian when you have the magnetic field pointing in the z direction? That Hamiltonian is equal to h bar divided by 2 omega L sigma z. Correct? This is just a generalization, right? Not generalization, I can say that. we map this to here. It just looked like now it's time independent, and we have something very similar, okay? And then I'm almost done, right? Next lecture, we will play with the tuning and look at the effect of each of these, right? I know it's tedious, but this is useful. I spent a lot of time to come up with this material because it's difficult to find a unified one. Yeah, okay. So that's all I have today.
Professor, could you put in the previous slide?
Yeah.
Yeah. Shift the matrix on the top. Is that because you said the same?
Shift, you mean this one?
Yeah.
Okay, I swap them,
Yeah.
right? Because, look at this. What is URF? Dagger. Is each equals to e to the power negative I omega 1 divided by 2 sigma z. So their matrix, I suppose, cannot do that because they might not commute, right? A times B not necessarily equal to B times A, right? But because this is sigma z, I can expand this as a Taylor series. In a Taylor series, you all be sigma z squared, sigma z cubed, right? Then what is sigma z times sigma z? You can swap them, right? So it means that sigma z times this whole thing is equal to this times sigma z. They commute with each other. That's why I can do that. Yeah, but I cannot do this for sigma plus, right?
That's what I'm wondering.
Yeah.
Otherwise, it would be like an identity.
Exactly. Yeah. So for sigma z is identity, but for the rest I cannot.
After doing the rotation.
You mean this one?
Yeah.
Oh, no, no. Here is, recall this is H.
Yeah.
This H is only to here. And then we apply, equal, no, not second part, the whole thing equal to H. Whole thing.
Okay.
Look at this is L, this is 1. Okay, this whole thing come here. Yeah, and this one is due to this term. Yeah. Actually, on Sunday. Yeah, it's not much. What is what? Up to next Monday. Yeah.
There could be everything till the
Everything until Monday.